We're done with the microelectronic component, we're done with talking about EMC for wires, both the internal and external inductance and resistance, both AC and DC. We've gone through what each component looks like. So you know what both inductors, capacitors, and resistors look like at high frequency. And I'll get your homework you turned in on Friday back to you. I don't have it all graded yet, so I'll get that to you on Wednesday. We're about to move into digital signals, and I want to mention one thing. Dr. Wentworth's book, he literally has about half a page about digital signals. Now, I want to tell you this much. Everything that you do in the real world that has to do with EMC and EMI, almost everything, is directly related to the type of digital signaling going on. Y'all know that like computers have roughly a gigahertz or better clock in them, right? A gigahertz clock means the actual on-time, off-time cycle occurs in 10 to the minus 9 seconds. But that's not the thing you worry about. A gigahertz, in terms of a clock, doesn't translate into that being a bandwidth or anything like that. People often do this. They say, oh, it's a gigahertz clock. Well, I don't have to worry about frequencies over 10 to the 9 hertz. It's the rise time. Y'all follow me on this? Has to do with how fast things change. I'm going to go through a little bit about this. Did anybody have me for signals and systems in here? If you did, then you know something about what I'm up to. But I have to make sure that you have an appreciation for the real problem. It is not the clock frequency you worry about, ever. It's always going to be the rise time primarily. So in general, when we have digital signals, now I'm going to just tell you, does anybody have any questions about resistors, capacitors, or inductors, or wires? All right, so you should know the internal and external inductance of wires and the internal resistance of wires. AC and DC, you should know what each element looks like in terms of its lumped element model. Y'all with me on this? So now we move into the next phase. So what affects these? So we have to talk about the mathematics of the digital signal and the frequency components of it. So in general, when you have V of t here, what you really do is have something like this. You're going to have a pulse that has a rise. Well, actually, I'll do it this way. I don't like doing it this way, but I'm gonna, because I'll do it his way. If this is the time axis here, when we talk about digital signals, it'll have a rise time, it'll have a time where it's on, it'll have decay time, and then the thing will repeat itself as such. Get a new marker. And if this is V of t, this will be the rise time. I think almost all of you know this. You've had this, I think, in digital electronics and probably in a couple other courses. Y'all know what a rise time is when you're talking about clock cycles, right? This would be the fall time. When we do analysis, we take the shorter of the two and we equate them. T rise equals T fall. Whichever one is shorter, we use. That's the worst. That's the biggest offender. Then we have something, and it's always done this way. It's at the point where the pulse is 50% its maximum to the point where it falls to 50% of its maximum. This is called tau. And then we have the actual pulse period. And you're used to seeing this, the actual duration of the pulse, to be capital T. Do you all remember that? Now, some people are going to see the capital T here. It's the period. In radar, it's called the pulse repetition interval, or PRI. Generally speaking, T is usually this accepted symbol in most junior level electronics courses. You all familiar with that, capital T? And in physics, I believe, they use that. So the frequency, and that's called F0 because this is considered the repetitive frequency is equal to 1 over T. So for instance, if you had a gigahertz clock, the period would be 10 to the minus 9 seconds, just to make sure. Now the rise time is the primary thing you worry about, and they usually almost always approximate it as a straight line. Fall time is a straight line too. So that's a trapezoidal wave. Y'all follow me on this? How many remember seeing something like this with who was it, Dr. New, in digital electronics? Did you do that? Where did you see this first? I'm trying to figure out. Was it in your digital logics courses or not? I don't know if they do that in digital. I'm just trying to get a handle of where, you saw it in your labs though, right?
Yes.
You had to, because.
Yes, in signals.
All right. That's a standard signal, T on that axis, voltage on that axis, standard. Now when we do an analysis of this thing, the usual way to do it, and I'm going to cut to the chase on you, Wentworth's book doesn't do any of this. He makes one simple statement about bandwidth. And you miss all that it involves. Now, if you're an electrical and computer engineer and you're working in the world of Wi-Fi, in radar, in communications, and in designing high-end electronics at high speed, you have to have a very clear understanding of what the frequency domain signature looks like. If you don't, you'll fall, everything you're doing may fall apart, all right? The assumptions you're making may be completely invalid. So if we go into the frequency domain, what I like to do is first go back to some basic frequency domain transforms. When we talk about like the Fourier transform of a signal, all right, that's generally the integral from minus infinity to infinity of f of t e to the minus j omega t dt. Y'all remember that? That's fundamental, right? And we would use this if it's an energy signal, correct? If it's a repetitive signal, then we use the Fourier series. And the Fourier series approximation would be for that signal v of t, it would be equal to a summation of c of n from n equals minus infinity to infinity, e to the j n omega naught t. Here omega naught would be 2 pi times f naught, where f naught is the fundamental frequency. And to calculate c of n here, it would be 1 over the period, an integral from minus t over 2 to t over 2 of v of t times e. And here it's going to be minus j n omega naught t dt. Now this is for an energy signal, this is for a power signal, right? We do a Fourier series analysis, and this would be for an energy signal, right? Because it's got a finite duration. Y'all remember that back in the day when we had signals and systems? Fourier series are used for repetitive series. If you got an infinite series, you can't have an energy signal because the energy is infinite. So what you do is you always talk about a Fourier series analysis, and then these coefficients right here have the power at each frequency. We talk about taking that and squaring that magnitude. Some of you remember this when you had COM, right? Communications? You didn't have COM? Some of you.
Yeah.
How many had COM? If you had COM, do you remember the signal power? It was either spectral, the energy spectral density if you had random signals and systems. That is in an energy signal, or the power spectral density if it's a repetitive signal that lasts forever. Y'all remember that kind of stuff? Basically, if it repeats itself forever, it's got an infinite energy, so we always talk about power. Okay, now, getting back to this, for that waveform, we have something that repeats, but we have a base signal right here we have to investigate. Y'all with me on this? So, let's take a look at this. When we take a look first at p tau of t, that's a signal that looks like this. That's tau over 2, minus tau over 2. A height, I just call it height A, but it looks like this. And this is t. This is a standard signal. I'm just going to say that this is really p of t. I'll make it 1 here. So it is the definition of p of t. Do you all remember that? That was a pulse signal. Another way to define it was rect. How many remember the rect function, RECT? And then you would put t over tau. So this p of t here is really the rect function of t over tau. Either one's correct. Now, when you did the transform of that based on this, you all remember what happened? What function did you get? How many remember? You don't have to say it. Yeah, you said it, the sync function. It's critical you know that. Whenever you have a pulse in time the transform, the Fourier transform of that would be equal to a sinc function. So the transform of this, if this is f of t, this would be f of omega. Fourier transform of that would be tau, right, times the sinc of omega tau over 2. And here, when I use the sinc function, sinc of x, I'm using the definition sine of x over x. Okay, so that's the sinc function. Y'all remember that? Now let's just take a look at this, the spectrum of it. And this is why it's so important to have an appreciation for this. If we plot just this, we'd have to square it if we wanted the energy density, or the energy spectral density. But just the spectrum of that would look like what? If this is omega, it would have a magnitude of t, or tau, at 0, correct, class? Now, where's the first 0? We just talked about this stuff. Where's the first 0 going to be? We know the sinc function, if we just take this, if we plot here, this function is going to be just magnitude of tau times the sinc of omega tau over 2 here. What's that going to look like? Kind of know, right? Almost everybody, it's going to look something like this. It would be symmetric, right? It's going to have this, and it's just going to keep going down. Y'all remember that, class? This the way, the general signature of the sinc function, the spectral domain. The key thing is, how do you get this first 0? Anybody? Look at the definition over there. The sinc of x is sine of x over x, right? So forget the origin at x equals 0. When's the next time sine of x is 0? Outside of x is 0. Plus or minus pi, correct, class? Plus or minus pi. So since this 0 right here will be when omega tau over 2 is equal to plus or minus pi. You follow the rationale for doing this? So if you do that, what do you get? Well, I'm going to take just the positive because I know this is an even function. So I get 2 pi over tau. It's going to be the first 0 here. And this 0 is, right here, is 2 pi over tau as well. Y'all with me? And that's in the omega domain. I'm just doing this, I'm using the omega transforms because you were exposed to those in signals and systems, right? And I'll be honest with you, omega is the most common thing. When we're doing frequency domain analysis, in the pure analysis section of it, it's always an omega or S. And then when we take it into the real world, we usually put it in terms of F, because F is something that we're familiar with, like the hertz, the 60 hertz and stuff like that. We're familiar with that. So if I look at this is omega. First 0 is here. Where would the second 0 be? Take a guess.
2 pi.
It would be with what? It would be 4 pi over tau, right? It would be twice that. Next 0?
8 pi.
It would be 6 pi, right? Add 2 pi. Y'all follow me on that? Right? So then, where's the first peak? Somebody's going to get this, because we're talking about this. Well, sine is what? Sine is 0 when x is pi. Then what happens? 3/2 pi, it goes to -1, doesn't it? So if we equated the argument omega tau over 2 to 3/2 pi, we get omega tau is 3 pi, or omega is 3 pi over tau, correct? I'm just going through the rationale for this, so we can figure out what this maximum is. This would be equal to 3 pi over tau in the omega domain. But now I'm going to make the point. Are you with me on this, guys, or not? How many are? I'm not trying to make this a long delay thing. It's not my fault. Anyway, when I come back here, what happens when we go in the frequency range? This is an important point. It directly relates to what Whitworth's book says. What do we have to do to omega to get it net? Divide by 2 pi. You with me? Everybody? Sure. All right, so what I'm going to do is now, I know that's 2 pi over tau. So in the omega, or in the F domain, it's just 1 over tau. So I'm going to put F here, because this is what Whitworth's book is talking about. This is really 1 over tau if this is versus F. And if it's versus F, omega, if you look here for 1 second, omega is 2 pi, right, F, isn't it, class? So if I put 2 pi F and divide by 2, I get pi F here. That was omega tau. This would be pi times tau times F. And then that would be 1 over tau right here. And this would be minus 1 over tau. Now remember, that's in the frequency domain. I'm going to ask you something. And here's where the word bandwidth sort of can mean anything to anyone. When you take the bandwidth of this signal, John, just listen. If this is centered at DC, probably it's just 1 over tau. Do y'all see that? This is DC, right? This would be 0 hertz, right? We know it's symmetric. There's no such thing as minus F in the real world. You always go from the center frequency upward, don't you, class, when you're talking about bandwidth? Y'all remember that if you're talking about DC? There's no such thing as a negative F. Right? So from here to here would be a logical bandwidth if we wanted to somehow denote bandwidth in a transient signature. Y'all see that, right? Now, here's the deal. Most of the time, when you have pulses like this isn't exactly that. We'll talk more about it. What actually happens is you have this thing being multiplied by a high frequency periodic signal. Do y'all see that? And that means this entire thing is shifted in the frequency domain. Now you guys had both AM and FM, right? You know, AM modulation takes what? It takes the spectrum of a low frequency signal, the Fourier transform basically, and it shifts it out to plus and minus the carrier frequency in the spectral domain. Y'all remember that? How many remember that? All right. You guys remember this for standard stuff? If you remember that, then you know one thing. If this thing is not at 0, but if it's at a high frequency carrier, then the logical bandwidth is 2 over tau. That's what they'll say, and that's what his book says, I believe. In his book, on page 517, I never liked this approach, by the way. He talks, actually it's 519. Well, he does use tau rise here, but he has sort of a hand-waving way to get there that I didn't even get to tau rise yet. Because you'll notice with this signal, tau rise doesn't appear. It's an infinite rise time. Y'all follow me on that, class? Infinite rise time. But you have to have an appreciation for this spectrum. So sometimes, if they talk about just that waveform in the bandwidth, they'll say F sub B is 2 over tau. You'll see this. Do you remember this from digital at all? Did digital use 1 over tau for a square wave or not? Does anybody remember? If you don't, it's okay, but usually there's very defined definitions of bandwidth. But what I'm trying to show you is there's no real bandwidth. There's spectrum, there's energy all up and down the band, isn't there? Just for that simple waveform. So when we use the term bandwidth, we have to be exact with what we mean. And usually, when they talk about bandwidth of pulse signals, it's between null to null in the first, this is called a lobe, believe it or not. I don't like the name, but that's what they choose. It's the main, actually the main energy holding region of the waveform, between the first nulls of that. That's called the lobe, and that's usually the bandwidth, and I'm just telling you that. I'm not sure I like that definition, but that's it. So now we go over to this waveform. You'll understand why I'm doing this in a second. Thank you. So next we're going to analyze that waveform a little bit. And here's where the fun begins. Sorry. Thank you. So, when I have this repetitive waveform, and we'll call this height just some V naught, it repeats itself over T. I like showing people this as much as I can because it's so valuable. There is a trick to get the Fourier transform, or Fourier series analysis of this. without doing a whole lot of integration by parts and everything like that, and it's so beneficial. You all agree that's a periodic function, it goes on forever, right? So intuitively, you know that I can write v of t as a summation for some c of n e to the j n omega naught t from n equals minus infinity to infinity. This is the exponential Fourier series, and c of n here would be equal to 1 over t, the integral from minus tau over 2 to tau over 2 of v of t e to the minus j n omega naught t. Omega naught here is simply 2 pi over the period, the fundamental period. Or it's 2 pi f naught, either one. Now, I want to say something. In general, engineers getting out of a program that haven't really thought about the best way to do this, what they'll do is analyze any waveform, and they'll get these coefficients. Those coefficients will have to do with the signal power density at every given point. The square of that C of n is the power density at any given frequency. But I want you to know something, and here's the important thing. When you look at that waveform right there, and this stuff, try to integrate this thing over a period, or just from minus tau over 2 to tau over 2. You're going to have integration by parts. Do you all see that? How many hate integration by parts? I hate it more than you, right? Anytime I can get around that, I do, and I have found a way to do it. So I'm going to show you this way. Some of you know this. If you had me, you already know where I'm going. So, and it requires me to first step back and show you something about impulse functions that is beneficial. So, before I show you the trick, I have to make sure you know this. When I take a look at delta of t, what is the definition of delta of t in your own words? However you want to do it. What is that usually? Something infinitely tall, in a sense, with a width that is infinitely small, where the product of the width times height is 1. Do y'all remember that? So it's basically, mathematically, it looks like this. Something where the height is 1 over delta t, and the width right here is delta t, and delta t is going to 0, right? And it's always centered at the point the argument here goes to 0. Y'all follow me? That's the delta function in a nutshell. But the delta function has a very, very important property. Y'all remember delta functions? Some call them Dirac delta, some impulse. It doesn't matter the term. You have to understand what they mean mathematically. Now, they're fictitious. They don't really occur, but we can approximate them certain ways. And here's a neat thing about a delta function. What happens if I take f of t and I multiply it times delta of t minus tau dt from minus infinity to infinity? This is called the sifting property. What does it do? I want you to please pay attention to this. This is so important. Well, this function, delta function, is 0 for all time except when this argument right here is 0, correct, class? And then it's infinite. When is this thing, I use the term turn on. When does the delta function turn on? Just look at it. When what? T minus tau is 0, right? Or when t equals tau. Do y'all follow me on that? Then the delta function turns on. Do y'all follow me? Now, when you're doing this integration with this delta function f of t, every other time, except the time the delta function is turning on, it's 0. So really, what this integration becomes is the value of f at tau times the integration of that delta function, which is 1, which means it's this. It's f of tau. And this is called the sifting property. Do y'all remember that for delta functions? It was the greatest thing, because if they'll try to trick you on some of these tests, especially when you get to your senior level courses. They'll have something, they'll have a cosine of omega t times e to the minus alpha t times like 1 minus t to the 9th, something crazy like this, times the delta function, delta t. And everybody's trying integrations every which way, they're wasting all their time. The truth is, the only thing that matters is the value of all the stuff adjacent to this delta function when it turns on. Here, it would be at tau. So you simply evaluate the adjacent function at tau and pull it out, and that's it. Y'all follow me? Now that's the sifting property, and it's very important, very important. Now we go over here. I'm going to try to do this in the most efficient way. So this is the waveform. I'm going to do one thing. I'm going to recreate this waveform, and I'm going to show you exactly how to go about the analysis where it's most beneficial, and also circumvent all the integration by parts that's usually required. You guys are going to need this stuff for some of your other courses. Did you guys do a lot of Fourier analysis and Fourier transform stuff in COM or not? Yeah. Usually the higher up you go, the more mathematically intense it gets in electrical and computer engineering. By the time you hit senior electives and stuff like this, you're doing a lot of stuff like this. So you have to be versed in it, familiar with it. So first, the function I have is like this. Right? That's V of t, correct? And this would be tau. This is the rise time. This was the fall time. And this was the time over which it repeats. And it just repeats itself going on forever, right? And I said that I could say V of t for that function was mathematically equal to a summation of C of n e to the j n omega naught t from n equals 0, or I'm sorry, from n equals minus infinity to infinity. And here, C of n is 1 over t, the integral from minus tau over 2 to tau over 2 of V of t e to the minus jn omega naught t dt. Now the truth is, when you do this integral, it can start anywhere, but it can only go over one period. That's the key. So when we're doing these coefficients, C of n, you have to only integrate that. The limits have to be over a total range of one period. Y'all follow me? Doesn't matter where you start or where you stop. Now that's V of t. Please watch this. This is where it gets interesting. Now what if I take a derivative of this? So if I take a derivative of V of t with respect to t, what do I get? I want you to please pay attention. I'm going to make this value A. The magnitude here is A. The reason I'm not using V is because you might get confused. So it's got a magnitude of A, all right? Now when I take a derivative with respect to time, what always happens to a function? What is the derivative with respect to time in your own words? Slope, right? It's the slope of the line, right? And if you look here, what's the slope from here to here? Yeah, what is it though? You're right. It's the rise is A, the run is tau, right? So it's got a value here of A over tau. Do you all agree with that? Y'all see that? It's just the derivative of this with respect to t. From here to here, it's the slope, right? The rise is A, goes from 0 to A. The run is tau rise. I'll put it tau rise, I'm sorry, tau rise. You all agree with that? Can you see it in the back, guys? All right, now, what happens from here to here? What's the derivative? 0. You all see it's 0. It doesn't change, right? It's constant. It's just 0, so it goes down to 0. Then up here, when I hit, and this would be tau. This is tau rise, by the way. Here, this would be tau what happens. Because look, I chose to go from 50% point here to here for a reason, because if you look at this, right here, this point is actually going to be tau away, isn't it? Just shift that down to the base right here. Y'all see that? So here it's tau, isn't it? Remember, this tau is the 50% point. So if you just shifted that down to 0 and didn't have this tau rise over 2 offset, you'll see that this point is tau. Do y'all see that, class? Okay. Now, What's the value of the derivative from here to here, from tau to tau fall, or tau rise? Let's just call it tau rise, because we're going to just use one of these two. Anyway, minus a over tau rise, right? It's important you see this. So now it goes down to minus a over tau rise. And it repeats itself. It just does that, repeats itself. Basically, it goes up, comes down, and repeats itself. And the only thing I'm trying to show you, this is a periodic function, and the height is a over tau rise. Does everybody follow me on what I'm trying to do here? Take a derivative with respect to t, you're going to get this, don't you? Now, is that a periodic function? Does it go on forever? Absolutely. That means I can write that. Well, that means my v prime of t is equal to some summation from n equals minus infinity to infinity of this, right? Well, when I take a derivative of this with respect to t, just take a look at this. This prime just indicates a time derivative. I get a jn omega naught out in front of c of n, don't I? So now I get jn omega naught right here times c of n times e to the jn omega naught t here. And this term is really like a c of n prime. All right, let me try to comment on this. You can replace this jn omega naught c of n by c of n prime. Therefore, you would have a Fourier series right there. Do you all see that? That's a constant coefficient times an exponential. And that means that constant coefficient, c of n, is given by that. Do you all see that? Everybody?
So it doesn't matter that it has a j in it?
Pardon?
It does not matter that it has a j in it?
This is defined, that c of n prime is defined as this. We don't know if c of n itself has a j or not. All right? It doesn't matter about the complex, if it's real or complex or a combination. It doesn't matter. So we get this. Now the delta function stuff is about to come in. So now I'm going to take one more derivative of this. You all see with respect to time? And the reason I'm going to do it is because I'm going to get some delta functions that are going to make my life very easy. So now I come over here. And now I've already got one derivative. Now I'm going to take the second derivative of that function with respect to t. Now take a look at this. This is the second derivative of this with respect to t. Please just give me your attention when you're done right. I want everybody to see this. This is so important. All right, I'm starting back here. I'm taking a derivative. What is the derivative of the function from here to here? What is the derivative? Let me ask you this. If I have a u of t function, it looks like this. That's u of t, right? Versus t. What's the derivative of u of t with respect to t? It is an impulse, isn't it? You all remember that? Because if you integrate an impulse with respect to time, you get u of t. All right, now that's something a lot of people doesn't click when you're first told this. But that means when I take this derivative, it's an impulse. It'll have a weight or a coefficient out in front of a over tau rise. So over here, it's real important. Now I get this. I get a simple delta function with a height of a over tau rise, delta of t, right? Now what happens at tau rise? This is real important. It's still 0 from here to here, isn't it? Because it's constant. Now in this time derivative, I go from here to here. So it is a delta function, but it's got minus a over tau rise. Real important you see that minus. So now it comes down like this. Still has the weight, and it's offset by tau rise. I'll just put it like that, okay? A delta function is located at tau rise, but it's it's negative. It's got the same magnitude, right? Keep going. What else happens? Now I keep going and I hit this point. That's at tau, what happens?
Goes down.
Another negative one of magnitude
Uh,
A over tau rise, right? But it's negative, and it's out here. So out here, I'll put it as tau. Let me just do this. Tau right there. Now it goes negative again, and it's going to have a value of minus A over tau rise, delta of T minus tau. Still not done. Now I come over here, I keep going, and what happens when I hit here? I go from a negative A over tau rise to 0, or it's an increase, so it's a positive delta. Does everybody follow me on this? This is going to be real important, especially on the final, that you have a clear understanding of why I'm doing what I'm doing. Not particularly doing this, but this relates to stuff you're going to see. So now, over here, and that occurs at what? Tau rise plus tau, right? So this is going to be at tau rise plus tau. It comes up here to A over tau rise, delta of T minus the quantity tau plus tau rise. And then it's going to repeat itself. So I don't need to just show it repeating, but at this point, if this was T, it'd just repeat itself. Do y'all follow me on that? How many see this? It's repetitive. Please try to focus. Now, the one thing about this is, that's got to be a Fourier series. Any repetitive function, periodic function, can be expressed as a Fourier series. So that means the second derivative of v with respect to t squared is going to be, and I can take a look at this. Here's the first derivative, right? So if I take another derivative with respect to t of that function, you see how I just get another j n omega naught right here? How many see that? With me on this? This is real important. People blow this too all the time. They don't see the simplicity of it. So that means this is the summation from n equals minus infinity to infinity of c of n, the original one, times j n omega naught squared. The squared happens to come from two derivatives with respect to time to get that impulse times e to the j n omega naught t. That's also equal to, and I can write it this way, same exact thing. And I can just put Cn double prime here, e to the j n omega naught t. And I can say Cn double prime is equal to the actual C of n that I want times this. So what I'm doing is I'm equating this inner term to a simple C of n double prime term. Y'all with me on this? Please try to stay focused. Some people just kind of, it's math. I don't like, if you're an engineer, you gotta love math. That's your life. You're smart mathematicians. Basically what engineers are. Very clever, smart mathematicians that know how to apply math to solve problems. Now I come down here, and I want to find that C of n double prime. It's a periodic series, so that means my C of n, and I'll put it here, my C of n double prime is 1 over the period. Then I go from minus tau over 2, actually you can go t over 2, minus period over 2 to period over 2 of that double prime series, e to the minus jn right here, omega naught t dt. And here's why the delta function is so important. I'm going to expand that, but just catch up. Now, this double prime is this. Right? This is V double prime. And if you look at that, maybe I better do it, I'll do it over here, because I want to make sure I make this point to everybody. Now when you take a look at that, my C of n double prime right here is 1 over the period integral from minus t over 2 to t over 2 of that double prime. Well, that double prime series has a constant of a over tau rise out in front. And then it has delta functions, delta of t there, and then minus delta of t minus tau rise there, and then minus delta of t minus tau there, and then plus delta of t minus the quantity tau plus tau rise here, times e to the minus j and omega naught t dt. Are y'all with me on that? I know it's a lot to write down, but I just literally put in the mathematics there of those delta functions. I want you to see it, everybody to see this. And now, here's why it's so good. Let me move this out of the way so you can see. This is a dt integration. All right? Remember what I said about delta functions? Are you having a hard time seeing what I wrote? Just tell me.
Yeah, what's the split in the board? What is that?
Right here?
Yes, sir.
Let me make it a little clearer. This is a delta function. It's a plus delta of t minus the quantity tau plus tau rise. And then it's going to be e to the minus j n omega naught t dt. I literally just put in the mathematics into that equation over there for C, or for, excuse me, for the double prime of V. All right, now look how you look at this and think, what next? All right, those are delta functions. Remember how I said the delta function, the only thing you look for when you integrate it is when it turns on, and evaluate what's ever next to it when it turns on, right? Take a look at this. What happens? My C of n double prime, now look at this. This is out in front. A, right, over capital T, tau rise. All those things are out in front of everything, right? Now, do the integration. Where does this turn on at? At 0, right? What's next to it that's a function of time? E to the minus jn omega naught t. T at 0, e to the 0 is? 1. That means this is just 1. This part of the integration is 1. Do y'all see that? Keep going, it gets better. What about this part? Where does this turn on? T equals tau rise, right? All right, so I got a minus, and then I evaluate this at tau rise, right? So it's minus e to the minus j n omega naught tau rise. Do you see this? How many see this right? This is nice, believe me. When you have to do this, and your boss asks you to do something like this, it saves so much time when you have this knowledge. So what about this one? Where does it turn on? At tau, right? It's got a minus sign, so it's minus what? E to the minus j n omega naught tau, right? Some of you already know where I'm going the next step. Now what's the last step? Right here. Plus, right? Where does this turn on? When t is equal to tau plus tau rise, right? So I have to take the e to the minus j n omega naught tau plus tau rise. Right here. And that is C of n double prime. I'm not quite done with this. Do y'all see what I've done? Now, some of you can guess where I'm going with this. If you know me, and you've had some of your courses, anytime you see a bunch of screwy exponentials like this, e to the plus or minus j anything, you think of trig functions, don't you? All right, y'all remember that? Sure, and if you look at this carefully, I'm just going to tell you what you can get, and you can factor this out. It'll be 1 minus e to the minus j n omega naught tau times 1 minus e to the minus j omega naught tau rise. I'll show it to you right here. We're getting there. We'll try to get this finished today. all right? I'm going to show you something. If you take 1 minus e to the minus j n omega naught tau, 1 minus e to the minus j n omega naught tau rise, and multiply them, what do you get? 1 minus e to the minus j n omega naught tau minus e to the minus j n omega naught tau rise, right? And then plus e to the minus j n omega naught tau rise plus tau. Y'all see that?
that second is supposed to be a tau rise.
What's that?
E to the minus j n omega naught tau rise.
You can put tau rise here, yeah. I'm sorry, it's this times that. Sorry, I didn't get it. Y'all see it? I can factor that, but I prefer to just show it to you here. Okay, now I come over here, and since I know that, I'm going to replace that with what I just showed you. Now, where am I going? Some of you know. Who had me for signals and system? 1, 2, 3. Some of you probably had something like this from Dr. New. I don't know, but this is a real clever thing. What am I going to do, guys? I'm going to turn that into a trig function. And here's how. Please remember this. This is so useful later down the road. You see how I have 1 minus e to the minus j n omega naught tau? Right? I'm going to factor something out of there. I'm going to factor an e to the minus j n omega naught tau over 2 out of there. So I have e to the plus j n omega naught tau over 2, or minus, pardon, minus e to the minus j n omega naught tau over 2. Now y'all see how if I factor this out of here, this times this is 1, right? And this times this is that. Now y'all see that? Why did I do what I did?
That's sine.
Because I know that the sine of anything is e to the j theta plus e to the minus e to the minus j theta over 2j, correct? So if I multiply this by 2j, I have exponentials of opposite arguments that have the imaginary part, and they're negative there, and you'll notice that's what I have there, don't you, class? So what does that become? That's 2j sine, isn't it, class? How many see this right here? Sure. This becomes equal to e to the minus j n omega naught tau over 2, and then it's 2j times the sine of n omega naught tau over 2, correct? Now, take a look at this next one. I'm almost done. What do you think happens there? Same exact signature, except instead of tau, you have tau rise, correct? Does everybody believe I can get a 2j sine of that? N omega naught tau rise over 2 out of it? You better believe it. So that becomes, I take an e to the minus j n omega naught tau rise over 2 out. And now I have 2j times the sine of n omega naught tau rise over 2. And that's what that Cn double prime, I know I'm out of time right now, becomes, but I want to tell you where I'm going. Those two sine functions and this are going to go in there, and then when I divide it by, to get the actual value of Cn, when I divide that by Jn omega naught squared, because that's over here, I'm going to go ahead and I'm going to create two sinc functions. And we're going to talk about this next time. But you're going to see this is really EMC analysis. We're going to get an actual signature, frequency signature. There will be no, oh, I wonder what the bandwidth means. You'll know exactly what the frequency signature of this stuff is. That's next lecture, and I'll show it to you. And then you're ready for EMC stuff when you talk about filtering and all that stuff, okay? So we'll pick it up next time. I'll give you